Speech coding. The objective of speech coding is to achieve savings in a required memory storage space, transmission bandwidth, and transmission power by reducing the number of bits per sample such that decode or decompressed speech is perceptually indistinguishable from the original speech. High-quality speech coders can achieve a big reduction in the bit rate by a factor of 13 or more, 13 bit per sample to 1 bit per sample or less, with no perceptible loss in quality or intelligibility. Specifically, speech coding methods achieve the following gains: a reduction in speech bit rate, or equivalently the same reduction in bandwidth, and the memory storage requirement, both of which are directly proportional to the bit rate. A reduction in the transmission power requirement because after compression, there are less bits per second to transmit. Immunity to noise, as error control coding method can be used to reintroduce some of the saved bits per sample in order to protect speech parameters from channel noise and distortion. Speech coding achieved a reduction in the bit rate by utilizing a physiology of speech production and psychoacoustic of audio perception. Namely, speech is correlated signal from an information theory point of successive speech sample contain a high level common or redundant information. The redundancy in a natural speech provides pleasant sound and robustness to background noise, speaker variation, and accent. However, speech redundancy can be modeled and removed before transmission and then reintroduced into speech at the receiver. Speech is generated by a relative slowly varying articulate system. Therefore, speech model parameters vary slowly and can be efficiently coded. Psychoacoustic of hearing. The threshold of a hearing and the spectral and temporal noise masking threshold can be used to allocate just sufficient number of bits to each subband in each speech frame to keep the coding noise mass below the threshold of hearing. Linear prediction and harmonic noise models in speech coding. Linear prediction model and harmonic noise model are two main methods for modeling and coding of speech signal. Linear prediction model is particularly good at modeling and spectral envelope of speech, whereas harmonic noise model is good at modeling and the fine structure of speech. The two methods can be combined to take advantage of their relative strength. In general, the main structure used for speech coding are this diagram shows the spectral envelope of speech model by LP modeled and represented by a set of LSF coefficients. The speech excitation modeled by a harmonic and a noise model. This figure shows the outline of a model-based speech coder. The speech signal is analyzed and its LP model, excitation, signal, and pitch are extracted. The LP model represents a spectral envelope of speech. It is converted to a set of LSF coefficients which have good quantization properties. The LSF coefficients can be scalar quantized, or more efficiently they can be a vector quantized using previously trained LSF vector codebooks. The most challenging part of speech coding is the coding of harmonic and the noise contents of excitation. To start with, unlike the extraction of LP model parameters, the extraction of fundamentals frequency is not straightforward matter. The main issues of modeling the harmonic and noise parts of speech excitation are the following: voice and non-voice classification, pitch estimation, estimation of harmonic amplitudes, estimation of noise variance, quantization of harmonic and noise parameters. In its simplest form, one can model speech excitation as the mixture of harmonic plus noise. More sophisticated methods employ different mixture of harmonic and noise for each speech sub-band centered on a harmonic. Modeling excitation for unvoiced speech. The excitation signal for voiced speech is composed of both harmonic noise. The proportion of harmonic and noise in the mixture around each harmonic. Frequency depends on the speaker, phoneme, and frequency. Generally, the proportion of the harmonic content of speech increases with the frequency. Code excited linear prediction coding. For applications such as mobile phones, speech coder utilize a form of code-excited linear prediction model of speech. As shown, CELP models speech as the output of filter excited by a combination of a periodic component and a non-periodic component. The principles of operation of SELP coders is the follows. Sampling. Before CELP coding, the input signal to the handset microphone is filtered and sampled at a rate of 8,000 samples per second. Each sample is then quantized with 13 bits per sample. The example speech is segmented into segments of 20 meters. This diagram is the outline of a simple code-excited linear prediction. The second is the linear prediction analysis. Each speech segmented is windowed and modeled by a 10th-order linear prediction model. The Z-transfer function of the linear prediction filter is given as the linear predictor coefficients are calculated using the Levine method. The predictor coefficients are transformed into line spectral frequency before quantization and transmission. The third is calculation of the periodic part of speech. The periodic part of speech is synthesized by exciting the linear predictor filter with a periodic input obtained from an adaptive codebook. A pitch filter is used to shape the periodic component of excitation. The pitch synthesis filter model has the following transfer function, where T is the pitch period and G is the pitch filter coefficient. For each segmented pitch, the period is calculated from the autocorrelation function of speech. Calculation of non-periodic part of speech. The non-periodic part of speech is obtained by exceeding the linear prediction model with the best noise-like excitation selected from a number of available noise code using an analysis by synthesis search method. The analysis by synthesis approach tells all the possible forms available and selects the one that minimizes the perceptual weighted mean squared difference between the original speech and synthesis speech. This analysis by synthesis part of the coding can also compensate for the deficiencies in the earliest part of the coding process. The fifth is reconstructed speech is passed through an adaptive post filter. This diagram is a code-excited linear prediction. This figure shows a more detailed block diagram of a code-excited linear prediction.